All right. Hello, everyone. I'm going to go ahead and get started with a little bit of solution stoichiometry. Considering we weren't able to do our live session as planned, I guess due to maintenance on the servers for OCPS, we're going to go ahead and get started. I just wanted to run through a couple of problems to assist you. Maybe you had some questions on them, or you wanted to make sure that things were in line and you were on the right track. Solution stoichiometry, again, mainly dealing with acid base and precipitation reactions is where you're going to come into this portion or this type of reaction. So let's jump in. I wanted to choose problem number 3 just because it looked like it could be interesting, just in case we run into questions or we're unsure of what's going on. Now I want you to note something. Even though it does not mention it, the easiest way to know, or just as a review, to know what your final answer is in this type of question, if there's only one solution given to you or one piece of information given to you, then you know it's based off of that answer. If you have two quantities, like we're looking at number 3, then you're also dealing with a limiting reactant problem. It doesn't ask anything about the excess, but at least we know whatever the limiting reactant is the one that's going to give us the least amount of product, which will be our final answer. So, problem number 3, 25 milliliters of 0.350 molar sodium hydroxide are added to 45 milliliters of 0.125 molar copper 2 sulfate. How many grams of copper 2 hydroxide will precipitate? So, taking a look at this, let's write out our givens. So we have 25 milliliters of 0.350 molar sodium hydroxide. Okay, and the next piece is 45 milliliters of 0.125. This is our copper 2 sulfate, so CuSO4. Now, we need an equation to work from here. So I'll go ahead and try to write it down here. We already know our reactants, NaOH plus copper sulfate. And it already tells us which of our products we're concerned with. It says that we're going to form copper 2 hydroxide, so CuOH2 plus sodium sulfate, which by our rules, our solubility rules, we know is going to be completely soluble, which in the future you'll hear me say has a high KSP value. But that's again later on. To balance this out, the only thing we need to do is add a 2, and we are set to go. Now let's go ahead and change pages, and I'm going to go ahead and change the color so it's a little bit easier to track. Now, if we're going to use our volumes and molarity, what we need to do is we need to change our volume into liters. So we do that by moving decimal 3 places to the left. 1, 2, 3. So we go with 0.025 liters of NaOH and the molarity is 0.350. So we have 0.350 moles per 1 liter. This is going to allow me to cancel out the liters for my sodium hydroxide, but it also still fits into our category in terms of molarity because molarity equals moles over liters. Now, we're supposed to get 1 mole of our product to 2 moles of our sodium hydroxide, so that's what's going down here. And since we're trying to find grams, that means I need to use the molar mass of copper 2 hydroxide. I've already gone ahead and calculated it, and I came out with 97.57 over 1 mole. So, taking a look, multiplying what's above the line divided by what's below it, 0.025 times 0.350 times 97.5, then divide that all by 2, and I came out with 0.42, oops, 0.427 grams of our product. Now, because of the fact again that it gave me a second quantity, that's what I'm seeing here, I have to do a second table. So my second table, going to go through the same process as I did for the first. So again, moving the decimal, 1, 2, 3. So put a 0 in there. 0.045 liters of copper sulfate, CuSO4, and 0.125 moles per 1 liter. This one is a 1-to-1 relationship to 1 mole. And my mass of my product is still the same, 97.57 grams over 1 mole. Multiplying what's above the line, dividing what's below it, I'm going to end up with 0.549 grams CuOH2. Now, if I'm taking a look at this, the question that I then have to ask myself is, which one is what my product is going to be? And that's, again, based off my limiting reactant. Well, which one gave me the least amount of product? That would be my sodium hydroxide, which only produced 0.427 grams. So my final answer is going to be 0.427 grams is going to be produced. Now, my hope is that this makes sense. Nothing so far that we've done has changed what we've done in the past or how we're going to proceed. But another way that you could easily look at this, you still have to have the math to back it up. But when we look at it, I'm going to get 1 copper ion, 1 copper 2 ion, to needing 2 hydroxides. So it's going to effectively cut in half my concentration that I'm going to need. That being the case, that's going to cause us to produce less of our product. Now, let's go ahead and move on. I want to go through one more problem and see if that'll help you out a little bit. And this one I chose just because I know some people will get confused because it adds in this hydrated compound. We have number 7. Now, number 7 says, what minimum number of grams of oxalic acid monohydrate would you specify for titration of no fewer than 15 milliliters of 0.1 molar sodium hydroxide? Both of the hydrogens and oxalic acid are replaceable in this reaction. So let's start off before we do anything else. Let's get the reaction. So I have oxalic acid monohydrate, so H2C2O4, and then it has a dot, H2O, and this was given to you in the problem, plus sodium hydroxide. Now, it tells you in the problem that both of the hydrogens here are going to be replaced. So I'm going to end up with Na2C2O4 H2O plus H2O. Now, you may be saying, okay, so why is this water not just thrown in with the water that we have over here? Doesn't make any sense. This water in this hydrated compound is actually attached or a part of the structure of this oxalate ion. So that's why we don't just drop it off. The easiest way to actually take that off would be to just heat the hydrated compound by itself. But that's another talk for another day. So let's go ahead and balance everything out. I'm going to need 2 of my sodium hydroxide and 2 of my water. In the end, everything else is balanced. So now that I have that, I'm going to use the information that I was given, my 15 milliliters of 0.1 molar sodium hydroxide, and that's what I'm going to use to figure out the other piece of information. So let's go ahead and get started. I have to change my milliliters, 15 milliliters into liters. So 0.015 liters. And just as I've done before, I'm going to do zero point 0.1 molar moles over 1 liter. Again, allowing me to cancel out my liters. So, what type of relationship do we have here? Well, it's 2 to 1. We have 2 of our sodium hydroxide to 1 mole of our oxalic acid monohydrate. And I'm going to abbreviate oxalic acid monohydrate as just OAM. Now, if I'm taking a look at this problem, I now need to figure out what is the mass of my oxalic acid monohydrate. So I'm going to take all of this, including the hydrogen here, and add up that to get my mass. I've already done it ahead here, and I got 108.06 grams. And again, this is over 1 mole. Taking into the example of what we've done in the past, I'm going to go ahead and multiply what's above the line, divide what's below it, and I came out with 0.0810 grams of our H2C2O4 H2O oxalic acid monohydrate. And this, because we don't have any other examples to look at, would be our final answer. Now, I hope that I've been able to answer any questions that you may have had, any confusions. If not, go ahead and leave a comment down below. I will try to get back to you as quickly as possible. Yeah, enjoy the new day, and I'm gonna write this out. Happy studying. Have a great day, guys.